Thanks, everyone. As Megan said, we live with electronics today that is not limited in the sense of functionality or even processing power, but limited in sometimes of its form. So it's not so much about Moore's law, but about how these systems are packaged. And in particular, we'd like to look at new ways of doing electronics. If we look at the ways in which people make electronics today, they're not creating these interesting fabrics. They're creating really what are boxy and rigid systems that are, as Privy spoke about earlier, they're made up of circuit boards that are then put into housings. Well, if you go back even further in the food chain, they start on wafer, which is in itself a rigid substrate. Those wafers are then diced, and then they go through the back-end packaging process, which puts them into lead frames and then into chips, and those chips are then soldered to boards. Those boards are put into housing, all to protect a very small amount of silicon that's actually at the heart of these systems, our phones, our computers, and everything else that we use in our daily lives. And so there certainly has been a transition over the past several decades for electronics to become smaller and more functional. Moore's law has done a wonderful series of things for us in terms of providing much greater performance year over year. But what we'd like to do is take a look at bio-inspired and conformal type systems, which we think can open up the use for these types of processes in many, many new applications, and literally taking it out of the box. There are three fundamental ideas in doing this. This is work that was done by John Rogers at the University of Illinois. He and his team have created a whole new class of systems that match skin, for example, in its modulus, its elasticity, and its ability to fold. And we'll show several examples of that. But one fundamental idea is that using MEMS-like processes, microelectromechanical systems that have been used for accelerometers and other types of sensors over the past couple of decades, is that you can etch silicon in a variety of ways and actually create flexible silicon nanoribbons. Now, silicon by itself is very much like glass, very brittle, very rigid, but you make anything thin enough, whether it be a 2x4 turned into a piece of paper, you can eventually make it thin enough so that it can be bent. And in this case, on the right-hand side, we move from the diving boards shown in the center images to interconnects that buckle out of the plane and can be put on pre-stressed elastomers. These are rubber-like materials. So we're no longer transferring electronics to FR4, which is what one of the big concerns in electronics today is all of the things that are added to that. But we're, in fact, able to do devices that are now on flexible substrates that can then literally strain and stretch in significant amounts, 100% or more in many cases. The second idea is, once you've created these flexible structures, how do you actually remove them from the wafer that you've created, where you can under-etch and release, also a well-known process, and then transfer those through a printing mechanism to this target substrate. So you go from the mother substrate to a target substrate, which can be any type of material. And we'll show several examples of that. In the lower left-hand corner, you can see a number of arrays of these micromaterials that can be released from the wafer and then printed to a target substrate using fairly conventional types of machines in order to do that. XY stages, pick-and-place devices, die bonders, at very small and precise levels, but very doable. The third concept is that of creating these stretchable interconnects, which are, in effect, these mechanisms that allow you to strain and stretch these devices. These serpentines that I show here, and below you can see some of the strains that are exhibited and shown in false coloring here, that enable that. And you can have, as I showed in an earlier slide, out-of-plane and in-plane type systems. So combining these three ideas, you can then create some really interesting new species of electronics. And so why is this important? Well, I hope to show you that these new varieties of electronics can now be used in ways we couldn't use electronics before. Perhaps improving implantable devices that were just spoken about, or putting on the body in a thin and conformal way that cannot be seen under your clothes, for example. So these silicon islands connected by interconnects can be used in homogeneous or heterogeneous arrays of sensors, computation elements, and so forth. And it's not necessary. What we don't want to do is reinvent all of the silicon that people have done today. The IP in silicon continues to grow rapidly, and there's a lot to take advantage of. And you can actually implement systems not only by making monolithic structures, but by incorporating COTS-type structures from existing devices and thinning them, and so that they can be incorporated into these systems. Here's, as we zoom out from that array, we can see the density of these interconnects, the fabric-like structures that result, that can be used in a wide variety of structures. Here, shown on a golf ball, is one such structure, so you get an idea of the scale here. But what's important to note here is that it's truly conformal, that it's not just covering the surface. If I took a piece of paper and tried to wrap an orange or a sphere, it wouldn't conform very well. You'd have wrinkles and so forth. It's the problem of the Mercator projection. But with a stretchable substrate, one that can strain and deflect, you can now actually cover that surface. I mean, not only that, but follow the ridges and the valleys of the surfaces on top of that larger scale surface. So the dimples in the golf ball can then be conformed to as well. And so this is a rigid substrate, the golf ball itself, but of course it can be an underlying flexible substrate that you can attach it to. And these arrays can be grown and created in the typical ways that the epitaxy is done in the semiconductor industry, and then transferred and printed to a wide variety of materials, including paper, vinyl, leather, fabric, and more. This is sort of an interesting set of materials, but it just shows that there is a wide variety of materials that this can be easily transferred to. And then showing the different types of strain that can happen in these particular printed materials. A close-up of one of them. This is the printed material on paper that you can add to. And why would this be important? Well, what if you had an LED array, for example, that you wanted to deflect and show as a flexible element? You can do that. You can have a large number of these devices that are woven together and then transferred and printed. And in fact, this could be separate. You can have a separate process because it's more economical to actually create a wafer of all LEDs and a wafer of interconnects and then combine them. So there are ways to combine these as well, so you don't have to do it in a monolithic fashion. This is a finger poking through an LED array. Now, we've had some interesting results with John's group where implantable LEDs have resulted in some very interesting emails and volunteers for, as human subjects, to have LEDs implanted in them. And I think there's certainly a market for that. But the point here really is not to show that we can put LEDs on your body very easily, but that we can put any type of electronics, whether it's a diagnostic device, a monitoring device, or even one that delivers therapy. In this case, together with the Gates Foundation, which is funding this work, is what we call paper diagnostics. This is being done in combination with Diagnostics for All, which is a nonprofit group looking for ways to deploy paper-based diagnostics in the developing world to be able to detect diseases. Microfluidic channels that are imprinted onto a piece of paper, then upon which are printed LEDs and photodetectors. And so you have chemical assays that allow blood and urine samples, for example, to be used in a way that when they react in the presence or absence of these diseases, that transmittance then becomes a function of whether that disease is there or not and to what level. And so this is a very simple way to deploy diagnostics in a very low-cost way without requiring complex or expensive electronics. You don't need to have an add-on to your smartphone, for example, or send it to a laboratory for assessment. Now, here's an example of where we're starting to look at interventional devices, catheters specifically. And this is a tactile array on a catheter in tubular form that can sense mechanical deformations of the heart in real time. And in this next video that you see here, you'll see a conformal array on the heart that's beating rapidly, and it's actually sensing in real time. And there'll be a short segment of showing the data from this. I think the important thing before I show this is to realize we're not looking at a couple of discrete electrograms on the heart. This is an epicardial application. We're actually looking what I think is a cinematic visualization of what is going on in the heart. And so that array is sticking to the heart, not through any complex adhesion principle, but van der Waals forces and surface tension. And then you can see on the bottom, as the red line traverses in time, this is actually it's much slower than real time. Those are in seconds on the horizontal axis. But each one of those pixels represents electrical activity at that particular point. And so we've transformed something from a very discrete sort of lub-dub signal that you might see in a typical heart monitor, now to something that looks at one particular region, a very small region, with hundreds, not single digits, of electrodes. And so what does that do? That allows us to reveal what the electrical activity on the surface of the heart, or the interior of the heart for that matter, what can be done with that. And what the clinicians and the researchers are looking at right now, or they're trying to interpolate from a few discrete points, but now we can do this in a much higher resolution way, both temporally and spatially. This offers a tremendous opportunity for us. This is a tactile array on the exterior of a glove. So it's printed to a vinyl glove and then pressed against the heart. So the surgeon now can have sensors in their finger that allows them to sense in real time what's going on on the heart. And those signals can be brought back and then visually displayed as well. So you're essentially putting pixels or eyes in your finger in a way that was not possible, not easily possible before. Again, those are printed and transferred. And this is a close-up of the actual array that was used on the heart. A little messy now with tissue and water and saline solution dumped on it during the course of the intervention. But you can see the various elements and the serpentine curves that allow it to stretch and flex as the heart continues to pump blood and move rapidly. This is an example of a catheter. This is an interventional device for cardiac applications. In particular, what we're looking at for this, and we'll be able to see this later if you wish. So I'm expanding the catheter out here, and it stretches. And there's a series of electrodes circumferentially around the balloon. This is not very dense. The image shows just a few electrodes, but here we have about a dozen, and we're building systems that have far more than that. We're able to map the pulmonary vein activity for the purposes of looking at ablation for the correction of cardiac arrhythmias. So these are sort of electrical storms of the heart that propagate through the heart, and we need ways in which we can actively short-circuit that, or rather prevent that from propagating. By ablating tissue in particular areas, you can stop those arrhythmias. So this is an application where the printed electrodes that are used on the balloon can be both used for the MAP and the ZAP part of arrhythmia correction through ablation techniques. The other interesting thing here, although these devices and the one on this prototype from last year are passive, we can actually add active CMOS elements in there to do things like multiplexing or diagnostics or provide other processing techniques right on the balloon. What we're trying to do is minimize the amount of material that we have to have traversing the length of the catheter into the back-end consoles. And so there are wireless techniques and other things that we can do with respect to that. So we've done a whole series of animal tests over the past year and a half, and a lot more exciting things are happening this year as well. So one of the also exciting things is perhaps a whole class of what we call epidermal electronics. This is a multifunctional device that has both an antenna, LED, strain gauges, temperature sensors. This one I'm showing on the image is functional. This is one of the systems that was built. This morning I actually took one of the Band-Aid type systems, and this is a non-functioning device, but I was able to place that on my skin. I don't know if you can see that, but you're welcome to ask me to show you my arm later. This is the same pattern that you see up here, but transferred to a bandage and applied just as easily as a Band-Aid. And now this can be externally powered through induction, basically field generation of power. Additionally, you can have communications with the device and then perform a whole series of things, including ECG, EMG type sensing on the body wherever you place this unit. And so this is starting to make you think about classes of monitoring systems for patients, for example, or athletes who want to achieve peak performance. And so there's a lot of interest in different fields for the ability to monitor people in real time, at high frequency, continuously, and to get good data from that. So it's not, again, small, discrete, low interval type reads. And so this is one, an earlier one with water-soluble PVA, which is the substrate that's carrying it. Now the elastomeric substrate here is only about 30 microns thick. The electronics layer is even thinner, less than 7 microns. So you can see that this is quite thin. It is thinner than a Band-Aid, much. And you can think of this is really a temporary tattoo, right? You're applying it in exactly the same way, but now you're able to deploy electronics on the body and show that. And finally, I think I just want to leave you with the idea that although I'm showing you some interesting health and medical applications, there are many more in energy harvesting and so forth that can be used with this. Even taking high-performance crystalline solar cells, creating fabrics of those so they can be deployed very easily and achieve performance levels that are not attainable today yet by organic systems, which are also potential flexible and stretchable substrate type materials. But human-computer interfaces, integrated personal power, again, the idea of resolution in time and in space, as well as the idea of body analytics, being able to mine information in real time from the body over large numbers of people, we think will lead to whole ways of doing clinical research and monitoring and sort of tagging inputs and outputs from people for monitoring their health. Thank you.